So lecture 29 today, again, a reminder, so today's Wednesday the 25th, we have exam 3 in 1 week, Wednesday, May 2nd. And Friday, May 4th, again, we will not meet, but I will make a video that you should watch for that class. But you don't have to come to class, I'll be gone. And then after that point, we've got 2 more weeks of class after that point, leading up to the final exam. Today, we're going to talk about an example we've talked about a little bit, but in more depth here, factor rings in the Gaussian integers. The Gaussian integers were complex numbers where the real and imaginary parts were integers. And you may have noticed in my speech for chapter 14 that I made some pretty cool graphs. We're going to look at those cool graphs here today in Mathematica. Review facts about ideals and factor rings. Then get back into irreducibility and reducibility theorems and the examples going into lecture 29b. You know, this class is very abstract, though, as I've tried to emphasize, there's plenty of real-life applications in the book, again, foundations of math ideas. But some of you like real applied stuff, and certainly actuarial math is real applied. Just a few notes about a couple things if you're interested in the possibility of being an actuary. Here at Bethel, at least this summer in 2018, we offer financial math for actuarial science. I teach that. It does help you prepare for actuarial exam FM on financial math. Actuaries to become fellows have to take a bunch of exams. It's in the ballpark of 10 exams over the course of a number of years. And certainly when you try to finish school, if you want to be hired as an actuary, it's good to have 1 or preferably 2 exams passed, one of which is on probability, and the second of which is on financial math, exam FM, on financial math. How is the course delivered? It's delivered online. I have made some video lectures. I haven't made as many as I want to make. I've made 4 one-hour video lectures that kind of overview the first 4 chapters of the book. I'm going to continue making more of those here, starting in late May, early June. And then I've got a bunch of problem-solving videos, typically 10 minutes or so. I've actually got over 100 of them made, which are optional, helping you learn how to solve problems to help you prepare for that exam. Another possibility, a little bit more comprehensively, is the UW-Madison. We just got an email the other day. They offer a 1-year post-baccalaureate certificate program. It's not a master's degree, it's a certificate program in actuarial science. If you want to apply for that for next year, it's due by June 1st. I'll forward the email to all of you. Obviously, if you're going to be at Bethel still next year, then you wouldn't be doing that, but you could think about it for them 2019, 2020. So you're supposed to be done with it within a year is the idea. I think I looked online briefly, and it looks like it's 5 classes is the required number of classes to get the certificate. Okay? So if you're interested in talking with me about either of these opportunities, I can talk to you after class, even today, if you'd like. Actually, for the Bethel class, it would be good if you're thinking about it to sign up soon, because we're trying to figure out bookstore orders, and we're trying to actually use last year's edition. They've come out with a new edition just in the last few weeks here. So, trying to get the book orders right. You could sign up soon if you're considering that, if you do want to take it. All right. So let's look at these factor rings in the Gaussian integers. I've got a couple motivations for this. One is it's cool kind of examples of rings and factor rings. Secondly, it does illustrate, again, continuing to try to understand things, as I always recommend with Mathematica, or some computer algebra system in general. And thirdly, is it's going to actually be a little preview of Friday's class, when we're going to get into chapter 18 on divisibility theory in integral domains, which is kind of a long chapter. It's kind of tough when you read it. And I think I told you to even skim it for today. I want to try to make it as simple as possible. It's kind of a long, tough chapter, but I don't want to, I'm going to maybe do a lighter treatment of it than I have been for some of these other chapters. Okay, so recall first of all, again, the Gaussian integer, Zi, is the set of all complex numbers, a plus bi, where a and b are integers. I is the imaginary unit, I squared equals -1, which is a unit in our sense in the field of complex numbers. And in fact, in the Gaussian integers. Complex numbers form a field, so every non-zero element is a unit. But also, even in the Gaussian integers, I is a unit. It's got a multiplicative inverse. It's negative I is its multiplicative inverse. But we also sometimes, just when you talk about complex numbers, you call it the complex or imaginary unit. Okay, here's something new. This is worth writing down, I think. The Gaussian integers form something called a Euclidean domain, ED. We've got the PIDs, principal ideal domain. This is an ED and a Euclidean domain. There's going to be another kind of domain I will talk about here in a few minutes, on which there is a function, little d, called a measure, or maybe you could call it a metric, might be another name for it, that maps non-zero elements of the Gaussian integers to the positive integers, and here's the key thing, in such a way that a generalization of the division algorithm holds with respect to d. D generalizes the ideas of both absolute value of an integer and the degree of a polynomial. And in fact, if you define D on the integers take away 0 to be the absolute value of a given non-zero integer, that will be an example of a measure. And if you define D on, say, well, the ring of polynomials with real coefficients, for example, to the positive or the non-negative integers, actually, in this case, you can define it to include 0. So this is not quite as good as it could be. D takes a polynomial and gives you back the degree of the polynomial. And you might remember, with thinking about the division algorithm both for integers and for polynomials, the key thing in the division algorithm with the remainder is that, well, when you considered only non-negative remainders, the remainder was less than the thing you were dividing by, assuming it's positive. If you were dividing by a negative number, the remainder, if you took it to be non-negative, would be less than the absolute value of the thing you divided by. And with the division algorithm for polynomials, the remainder had a degree less than the degree of the thing you were dividing by. So this is what I'm hinting at when I say D allows us to generalize what the division algorithm says in a more arbitrary kind of setting, a more abstract kind of setting. And Zi is an example of a Euclidean domain. What's the measure in this case? It turns out to be a squared plus b squared, which is essentially the square of the distance of the complex number a plus bi from the origin of the complex plane. If you think about the Pythagorean theorem, you think about the complex plane. With a real axis and imaginary axis. By the Pythagorean theorem, draw a right triangle in here. This distance there is square root of a squared plus b squared. Square that, you're going to get a squared plus b squared. So this is the square of the distance between the complex number a plus bi and the origin. So there's some sort of generalization of the division algorithm that's going to work in the Gaussian integers. Probably on Friday we can be more specific about what that means. It also turns out, though this takes proof, that because of this, Zi and other Euclidean domains, for that matter, can be shown to be a principal ideal domain. We are assuming we're dealing with commutative rings with unity here, by the way. We already talked about principal ideal domains. They are, and we're talking about integral domains too. They are integral domains, no zero divisors, in which every ideal is a principal ideal generated by one element. Right? It's analogous to a cyclic group. It's a PID. But remember, even though the notation is the same and the idea is kind of similar, the principal ideal generated by an element in general is not necessarily the same as the cyclic group generated by that element under addition. They can be different sets. With the integers, they're the same, but with polynomial rings, for example, they're different. And it can also be proved, this takes proof, to be something called a unique factorization domain, UFD. Okay, so we have ED, PID, and UFD. Every ED is a PID, and every PID is a UFD, it turns out, in abstract settings. And it kind of is very fortunate that goes in alphabetical order. E, then P, then U. What is a UFD? It's something, it's a domain, an integral domain in which an appropriate generalization of the fundamental theorem of arithmetic holds. What's the fundamental theorem of arithmetic? It's unique factorization, unique prime factorization, right? So there's, in a unique factorization domain, there's some generalization of that. We can factor any ring element somehow as a unique product, or should I call them primes? We're actually sometimes going to use the word prime, and sometimes we're going to use the word irreducible. Sometimes they're synonyms, and sometimes they're not. Irreducible, like we've been talking about with polynomials. Since the Gaussian integers form a PID, and the ideal is a principal ideal, it's of the form that's generated by a single complex number from the Gaussian integers, a plus bi, where a and b are integers. Within a given principal ideal, you know you've got a principal ideal, and you want to find a generator, say? A generator would have minimal measure. In the complex plane, it would be, if you thought of the points in the ideal as being points in the complex plane, and they would be, with integer coordinates, pick an element in that ideal that's closest to the origin, and that would be a generator. As in the solution key for the completion homework from chapter 14, it's quite interesting to represent cosets in factor rings visually, and there's a typo there, right? This is something I think I can update here. Zi mod by a plus bi. Visually, as we are about to do with Mathematica. All right, let's go ahead and do it. So under this new stuff heading, we already looked at these examples of factor rings, where the original ring was a polynomial ring, Z2x and Z3x. Now let's consider examples like this. Zi is the Gaussian integers. We're modding by principal ideal generated by some Gaussian integer. Example 1. What if we mod by 1 plus the principal ideal generated by 1 plus I? Okay, so I'm not going to, for the most part, I'm not going to write on the board here. We should look at what I wrote in Mathematica. I'll try to highlight some things. You might want to write this down to some extent, but I will save it for you in the course folder on Google Drive. First of all, what form do elements of this factor ring take? They're cosets, so they take that form. An arbitrary Gaussian integer, a plus bi, plus the ideal. It's worth noting, okay, so what does that look like in terms of representatives, so to speak, or simplified representatives? Well, okay. What am I trying to say here next? I'm trying to think about, simplified coset representatives in a sense. And the way I'm doing that is I'm thinking, first of all, about what it means to be in this principal ideal. What is the principal ideal? Right on the board here. Principal ideal generated by an element A in a commutative ring with unity. is the sum of all products of this form as R varies over the ring, and that will be a two-sided ideal when the ring is commutative, as these rings are. You could also define it this way. When the ring is commutative, these are the same thing.
Oh.
So I'm really taking my A, so to speak, which is 1 plus I, and multiplying by R, an arbitrary ring element here, and seeing what kind of form the product has. It has this kind of form. It's a special kind of form. Any Gaussian integer that has this kind of form is going to be in this ideal. That's got a solution for some A and B. There's another way to think about it. And you can solve for A and B. This is a system of linear equations in A and B that you can solve for A and B in terms of C and D. And what this ultimately allows you to conclude is that there will be a solution if C and D are both even or both odd. They have the same parity. C plus D and D minus C are both even, which means C and D are both even or both odd. You're dividing by 2 there, is the reason. You want these to be integer solutions. In addition, you could also say it means two cosets like this are the same if and only if the difference of the real parts of the representatives, A minus C, and the difference of the imaginary parts, B minus D, have the same parity. They're both even or both odd. Okay, so there's a way to think about it symbolically. Then I've got this Mathematica code that allows me to ultimately visualize this factor ring. I got these functions that I'm calling coset generator and coset plot. Down here I call it CP. I better call it CP again. CP stands for coset plot. So I'm making Mathematica functions that are going to generate the cosets, finite versions of them, based on a certain representative. Because you could, so for example, you could ask, what's the coset that contains 1, 0, meaning 1 plus 0 I, the number 1. What's the coset? Well, what are some elements of it? There are a bunch of elements in it. If you take the first coordinate of any of those elements and subtract 1, and take the second coordinate of any of those elements and subtract 0, you should get two things of the same parity. So for example, negative 12 minus 1 is negative 13 is odd, and negative 7 minus 0 is odd. Should work for any of these. Which is, if you look over it, meaning that in each case with these points, they have opposite parity. Odd, even, even, odd. That should make sense. Anyway, that generates a list of points in the coset. Then the coset plot will plot them, CP, 1, 0, for example, with a certain color, like blue, and a certain point size, like 0.05, for example. Makes a plot. Those are too big. 0.01. There they are. And then this is combining some plots to see distinct cosets. So what's going on here? What's this about? The red dots form one coset in the factor ring. The blue dots form a second coset. It's a 2-element factor ring. This is visualizing 2 elements, red and blue. All the red and blue dots are equivalent to each other in the factor ring. They're part of the same equivalence class, the same coset. All the blue dots are effectively the same 0.2. They're in the same coset, the same equivalence class. It's a 2-element factor ring. So is it isomorphic to Z2? It does turn out to be isomorphic to Z2, though that actually is not. It's technically something you need to check. So you can always in rings, you can always define multiplication trivially if you want to. It's kind of a weird thing about rings again. You can define the product of any 2 ring elements to always be 0. Assuming the ring doesn't have unity, then it would make sense. And it would still satisfy the axioms of the ring. So there's kind of weird examples like that again. But this one does turn out to be isomorphic to Z2. You could consider which simplified coset this equals. And you can think about it symbolically. You can also just look at the picture. 7 plus 5i. Where is that dot? 7 plus 5i. The real part's 7. The imaginary part's 5. It's a red dot. 7 plus 5i is 0. The red dots are the zeros. Red dots represent the 0 element of the factor ring. A little bit more interesting if you consider other kinds of ideals to mod by. Here's example 2. Mod by the principal ideal generated by 2 plus I. You could once again consider, okay, what does an arbitrary element of the ideal look like? Based on multiplying R times A, so to speak, like I have on the board. Arbitrary ring element times the generator of the ideal. The real and imaginary parts have this kind of form. So what does it mean for a Gaussian integer to be in this ideal? It means this would have a solution for A and B being an integer. You can solve this system in general like this, which means if you want these to be integers, 2c plus d and 2d minus c better be divisible by 5. Which is what I say here. And you can do more calculations to verify more things, like when are 2 elements of the factor ring equal. Again, it's related to being divisibility by 5. So does this mean the factor ring is isomorphic to Z5? Well, that's not completely obvious. Here I do need to re-enter this coset generator stuff, because actually I'm constructing it differently. The formula that I have here is not the same as the formula that I have here. As you read through it, you'll see why. Anyway, if you go through this Mathematica notebook, you do need to re-enter this code every time. The CP is actually the same, but the coset plot. But the coset generator code is different. Anyway, you already see the picture here. We do have 5 elements in the coset, distinguished by different colors. Red is the 0 element. Blue is the multiplicative identity, the 1. Notice it goes through 1, 0. The red one goes through 0, 0. Then we've got 3 other ones, green, magenta, and cyan is that color there. Different colors, different sizes, so you can distinguish them better. This is a representation, a visual representation of the factor ring. Zi mod the ideal generated by, what was it, 2 plus I think? And it would tell you, just looking at the picture here, that, for example, this element, 6 plus 2i, plus the ideal in the coset, is the same as a simpler representative is 2. 2 plus that coset is a simpler representative of the same coset. 2 plus the ideal. You can actually also even visualize certain products here. An interesting thing to realize about this diagram that I just showed you, don't write this down, but just think here, is that it is forward invariant under counterclockwise rotation by 90 degrees, and along with an extension by a factor of 2. What rule does that mean? Well, it means if you take the entire diagram and you rotate it by 90 degrees, and then you expand by a factor of 2, meaning move points twice as far away from the origin from where they started, it will be invariant, meaning red dots will get mapped to red dots, blue dots will get mapped to blue dots, and green dots will get mapped to green dots, etc. Now I made some code that did this, though it runs kind of slowly, and I created something that I called small coset generator, so I didn't have as many points, so I didn't run quite as slowly, but it still runs quite as slowly, so I don't include all the points here, only the red and blue dots, except where are they? I must have forgotten something here. I see I have something that I called points here. What was points? points. Well, I think points might have been the join of these different lists. I wonder if I forgot to save this correctly. This might run too slowly. Okay, it is just red and blue dots. Okay, so that's good. It still went a little slowly. So what do we have here? We have a smaller grid of points, 2 cosets from the 5 coset set. And I've got an animation parameter that I'm going to slide to the right here. And what you're going to see is you're going to see a rotation and an expansion. And make sure you take note of where this blue dot, for example, goes. I'm going to rotate by 90 degrees and expand by a factor of 2. It should go to that point. And double check it before class. I hope that works. This point here, rotated by 90 degrees and moved twice as far away from the origin, should go to that point there. Watch it here. Watch that second example. So I think this point with coordinates, which is representing 3 plus I, should go to negative 1 plus 4I. Oh, wait a minute. No, it should go to this one, actually. Negative 2 plus 6I. Let's see if that happens. Watch it. Oops, need some errors, but yeah, negative 2 plus 6I, it's there. Watch it again. Ignore the errors. I'm not sure why those are happening. But at least we're seeing the picture. Watch that blue dot that's at 3 plus I. Rotates and goes away from the origin. And it ends up at negative 2 plus 6I. Rotated by 90 degrees and twice as far away from the origin. Why? Why is it doing that? I'll let you look into it if you like. It's based on the geometric properties of complex number multiplication. A few of you might know about that, but some of you may not. One more example is even more complicated, so I don't want to explain this ton, but what if we modify this principal ideal? Then it turns out the factor ring has 8 elements, and it can be visualized with 8 different colors. So here I was modeling by the ideal generated by 2 plus 2I. Which, by the way, is red there, meaning it is 0 as well, 2 plus 2I. 8 different colors, red, blue, green, magenta, cyan, orange, brown, and black, of 8 different sizes here. 8 elements in the factor ring, 8 cosets. And you can try to visualize things in various kinds of ways. Okay, makes pretty pictures, and I think it's also enlightening to think about. Am I going to test you on it? Well, not these pictures, but I might test you on something about factor rings like this. I wouldn't make it too terribly difficult. I think I'd give you some guidance or something if I did make up a question about it. I'm not sure what that kind of question would be at the moment. All right. Let's move back to the PowerPoint now. Quickly go through the next few slides. This is actually a review. So again, maybe you want to just sit and think. Okay. Leading back up toward irreducibility and reducibility, which it's looking like we're not going to get to until after the quiz here. Reviewing, polynomial rings with coefficients from a field are PIDs. That's a theorem that we should know. If f is a field, then f of x is a PID, which is good. Again, principal ideal domains are relatively simple. As I've said before, Even though F is a field, that doesn't mean that's a field. It's not going to be a field. In this ring, elements of degree higher than 0 don't have multiplicative inverses. They're not units. Linear, quadratic, cubic, etc. Polynomials will not have multiplicative inverses. But it is a principal ideal domain. We went over the proof last time. We'll not go over the proof again. Reminding you of some other things. Criterion for A to be equal to an ideal generated by one element to be a principal ideal. The proof on the preceding slide also essentially proves this fact here. If you got a field, and A being a non-zero ideal in the field, and in this factor, in this ring, this polynomial ring, and g of x is an element of the polynomial ring, it is a polynomial, then A is generated by that element if and only if g of x is a non-zero polynomial of minimum degree in the factor ring A. Now, if g of x were a constant polynomial, you should also think about this too. If g of x were a constant polynomial here, you should also realize that would mean a non-zero. That g of x would be a non-zero constant polynomial. It would be a unit. It would have a multiplicative inverse, since f is a field. And that would mean, by those facts about ideals that I said you should work on memorizing, that A would actually be all of the entire ring. Right? If an ideal contains one, or if it contains a unit, then it actually equals the whole ring. So in this situation, if g of x is a non-zero constant polynomial, A will actually equal f of x. Otherwise, if A has no non-zero constants in it, no non-zero constant polynomials, it's going to have some polynomial minimum degree. It could be degree 1, it could be degree 2, it could be degree 3. Whatever the minimum degree is of any polynomial in A, it will be a generator for A. It's a fact worth remembering as you read and study and try to understand this. I don't want to prove this completely before the quiz, because we've got the quiz I'm going to take it in a couple minutes here, but this isn't really a criterion for A to equal principal ideal, but it's an example of a factor ring that's mentioned in the book and is worth briefly thinking about. And is also maybe worth thinking about in terms of the first isomorphism theorem. I claim this factor ring is isomorphic to the complex numbers. Which means it's going to be a field, first of all. Which means also x squared plus 1 will be irreducible in over R, which should make sense. Its roots are plus or minus I. Imaginary unit. So the maximal ideal, because the polynomial will be irreducible over the field. If you had to prove this fact, how would you do it? You can use the first isomorphism theorem. You can come up with a homomorphism from Rx onto C, which hopefully has a kernel equal to this ideal. And then apply the first isomorphism theorem for rings. What would be the most natural homomorphism to think of here? Take an arbitrary polynomial with coefficients in R and map it to a complex number? What would you guess you do here? Let's call this f of x. Is there a most natural thing to do here? If we want the output of this mapping to be a complex number, the A's are real numbers. I don't see any complex numbers in there. I'm going to get a complex number output here. you know, Jacob?
You plug in I for x.
Yeah, replace x with I. That's exactly what to do. We talked about this kind of homomorphism last time. Plugging in a number, except I think we were talking about plugging in real numbers, but we're plugging in the imaginary unit here. This will be a complex number. It's the most natural thing to do to actually get a mapping like this. Is it onto? Yeah. Because phi of a plus bx, for example, would be a plus bi. What's its kernel? Everything that gets mapped to 0. Certainly, x squared plus 1 gets mapped to 0 because you get I squared plus 1. Negative 1 plus 1 is 0. So certainly x squared plus 1 is in the kernel. If you think about it, if your polynomial's got real coefficients, there's going to be no smaller degree polynomial in the kernel. The kernel will contain the ideal generated by this. And it also does turn out that every polynomial that gets mapped to 0 here will be a multiple of x squared plus 1. X squared plus 1 will be a factor. So the kernel does equal this principal ID. And then you can apply the first isomorphism there. Let's say these are isomorphic. So this is a way to construct the complex numbers with factor rings. And it's a helpful way of thinking about it sometimes. All right, let's take the quiz.